Okay, so this is lecture number 2. I will just add here number 2. Okay, so this is about system with 2 or more degrees of freedom. And then the first part of this chapter will be about the free vibration, in which we will find in the free vibration the nature frequency, mode shape, and the response. So the additional part here is the mode shape or normal mode. And we started with the example number 1, okay, in which there are 2 masses. This is a 2 degrees of freedom system, and expected that we have, of course, 2 natural frequencies and 2 normal modes. The modes or the normal modes are associated with the nature frequency. Okay, so first of all, we put the direction for the positive direction for x1 and x2, the coordinates, and assume that x1 greater than x2, or you can assume the other way, it doesn't matter. You can put x2 greater than x1. Okay, here we assume x1 greater than x2, and then we put the free body diagram. Then we apply Newton's second law on each mass, and we find the equation of motions, which are second order ordinary differential equation. The system is the n-damped system. And the solution is harmonic, is assumed to be harmonic for each mass who is oscillating with different amplitude, but the frequency is the same. So x1 equal to a1 sine omega t, and x2 equal to a2 sine omega t. So they have different amplitude, but frequency is the same. Then we substitute this assumed solution in the differential equations, and we get 2 algebraic equations in which there are 3 unknowns, a1, a2, and omega. So in order to see how we can seek the solution, we put this in matrix form. And as you can see, it is the matrix, coefficient matrix multiplied by vector a1 and a2 equal to 0 and 0. So in order to satisfy the right-hand side, it means a1 and a2 equal to 0. This is one solution, and we call the solution trivial, which means there is no vibration. The other solution is the determinant equal to 0 of the coefficient matrix. And from here, we get the characteristic equation. We put lambda equal to omega square. Lambda is the eigenvalue, where omega is the initial frequency. So lambda equal to omega square will reduce the equation of the determinant into into quadratic equation and lambda. Quadratic equation mean there are 2 roots, lambda 1, lambda 2. Okay, and we number lambda 1, lambda 2 from smallest to the highest. So lambda 1 is 0.634 k over m, and lambda 2 is 2.366 k over m. And then you take omega 1 is square root of lambda 1. We don't take the minus, we only take the plus to get the natural frequency. So because natural frequencies are always positive. And this is one thing. We found the natural frequencies, which is the important part that we need in the free vibration. The value of A1 and A2, we cannot find them exactly because we have only 2 equations, but what we can get is the amplitude ratio. Okay, so from those 2 equations here, or here, okay, you can get A1 over A2, either from the first equation or from the second equation, because they would be the same. Okay, so A1 over A2 equal to K over 2K minus omega square M equal to 2K minus 2 omega square M over K. And then we substitute here in the amplitude ratio to, with omega equal to omega 1. Okay, so the equation for A1 over A2, if you take the first one, you have K over 2K minus omega square M. When you put omega equal to omega 1, we find the amplitude ratio of the first mode, which means when the system is oscillating with omega 1, you will have A1 over A2 equal to this value, 0.731, always, regardless of time. Okay, as you can see, there is no time here in this equation. And we write A1 over A2 superscript 1. Superscript 1 means for mode number 1. And when you substitute, you get 0.731, which is positive value. And this means this is always, regardless of time, this ratio is the same. Then we put omega 2 in the amplitude ratio, and the amplitude ratio is given here as superscript 2, which means for the second mode. Okay, and we get minus 2.73, which is negative. Okay, now we talk about the normal modes, or called eigenvectors. The normal modes, mathematically in linear algebra, you will call them eigenvectors. The normalization we will use, as we said, that ratio we have. So if you assume that A2 is 1, for the first mode, this is phi 1, is the eigenvector, is 0.731 and 1. It's a vector, right? When you put A2 equal to 1. This is a way of, you can put the other way. You put A1 equal to 1, and then you find how much is A2 from the ratio. Okay, but the normal modes or the eigenvalues, sorry, eigenvectors, we will follow that A2 equal to 1. Okay, so phi 1 is 0.731 and 1. The second eigenvector is minus 2.731 and 1. So you can see that always we are putting A1 equal to A2 equal to 1. This is one way of normalization. Other methods will be, finding the dividing by the maximum, sometime. Okay, so this is what it is followed by this textbook. Okay, the normal mode analysis is now in each mode, normal mode oscillation. We can write the equation of the response. If the system is oscillating for first mode, you will write x1 and x2 as a1 times the eigenvector number 1 sine omega 1t plus psi 1, if it is oscillating with omega 1. And the second response equation for the second mode is x1 and x2 equal to, this is also to be A2. Okay, A2 minus 2.731 times sine omega 2t plus psi 2. And this is called the normal mode or mode shape. Okay, so for the mode shape, for the first mode, this is first mode. We have, those are nodes, external node, because the springs are fixed here, and they are called external node. And this is also external, which is that x1 and x2 here are always 0. Okay, or the displacement at those points are always 0. So if A1 if A2 is 1, A1 is 0.731. Okay, so the normal mode, we can extend it. For the first mode, we have node here and node here, and this is the location of 1 and 2 and 1. Okay, so if A2 is 1, this is 1, then A1 is 0.73. Then you can join the points together. Straight lines. And if A2 is -1, then A1 will be -0.73. Here is, say, this is -1. This will be a -0.731. And then again, we join the points together with the straight lines. This is the first mode. And this is called mode shape of the first mode. As you can see, this is similar to the simply supported beam, although that was a continuous, but all the two masses are moving in the same direction. Okay, so the two masses here are in phase, which means they move together in the same direction. For the second mode, when A2 is 1, A1 is -2.73. Okay, so you can, for the second mode, again, we have the external nodes, and here is the position of mass, second mass, and this is the first mass. So if it is 1, if A2 is 1, A1 is -2.7. Okay, I'll put it on this side. And then you join the points together. So this is -2.73. And when A2 is -1, then A1 is 2.7. And then you join the points together. So as you can see here, we have internal nodes. Now this is the location of M2, 2M, and this is the location of M. So there is a point on the spring in the middle is has always 0 deflection or displacement at all time. So here is the second mode, and we have the two masses are moving out of phase. Which means they move in the opposite direction. So for the spring in the middle, the springs on the other on the ends are either under tension or compression. They are when the mass is moving for M, when the mass is moving to the right, the spring is under tension. If it is moving to the left, it is under compression. Okay, for the spring between the two masses, this is the spring that is under severe loading. Okay, so let's say that we have, this is the spring when it is at under no stretching. Okay, so when it is when the two masses, there is a point here maybe near the middle. Okay, this point, when the spring, when A2 is 1, it means it will move to this point, right? And this will be A2 is 1, and this will A1 will be minus 2.7. Okay, but this point is always 0. So here it is under tension, this part. Tension, and this part is also under tension. Okay, but this point is always 0. Okay, and then when A2 is minus 1, it means this will move here. And the point, the end point on the left side will move even closer. This is 1, and that will be 2.7. So this will move more. Okay, so okay, so here this is the, let's say, the 0 line. Okay, this is moving 1 here. This will be moving from here minus 2.7. Okay, so this will move minus 1 here, and this will move minus 2.73. Okay, so this is compression and compression. Okay, and this point is always 0. Okay, this point is always, displacement is 0. This is the node. Which means 0 displacement. And this makes the spring highly active and under loading more than the other two springs. Okay, if you have no questions, we move to example 2. Okay, example 2 is about pendulums. بقيت اللي انت احمد راحوا الشباب.
ما ادري دكتور.
Okay. Okay, this is called, the example here is about called coupled simple pendulum. Yeah, so if you take, this is the main problem here. If you take a pendulum alone, the two pendulums, if you remove the spring, those are simple pendulum, and the meaning of simple pendulums is that we have this is a massless rod. Okay, massless rod. The same thing here, this is massless rod. And we have bulb masses. And this is the simple pendulum. Now they are coupled by a spring. This is the coupling spring. If you remove the spring, the two pendulums will oscillate independently. So this is the spring is the element that is joining the two pendulums together and make them as a 2 degrees of freedom now. You use theta to give the motion theta 1 for the pendulum on the right, and theta 2 is the angular displacement of the pendulum on the left. So theta 1 and theta 2 are the two independent coordinates, and we'll assume that theta 1 is greater than theta 2 in order to draw the free body diagram and then obtain the equation of motion, and do the same analysis as we did in the example number 2. So the system here is rotational, while the system in example 1 was translational. Both are 2 degrees of freedom. Okay, let's take the free body diagram of the pendulum on the right side, which is pendulum number 1. Assuming theta 1 greater than theta 2, then the spring force, and the spring is unstretched when theta 1 and theta 2 are 0. So we can put this as a comment that the spring is undeformed or unstretched when theta 1 equal to theta 2 equal to 0. So when it is in equilibrium, assume the spring is unloaded. So the spring force is 0 at theta 1 equal to theta 2 equal to 0. Okay, at arbitrary position, when pendulum 1 is at theta 1, then the spring force will be, the two ends of the spring are moving. So this will be with small oscillations, of course, we'll assume small oscillations. So that sine theta, okay, let theta 1 very much less than 1, and theta 2 is also very much less than 1. Then the spring force will be Ka theta 1 minus theta 2. Okay, so the spring, when it is unstretched, and then when it is moving, then this will give us a distance, and this will give us another distance. Okay, the distance on the left side is A, because A is this distance, the location of this, the location of the spring on the bar from the pivot. So the distance will be, the horizontal distance will be A sine theta 2 here, and we will assume that it is theta 2. And this point will be A sine theta 1, and sine theta 1 is theta 1. It's like X and Y. Remember, in the basic citation, we have X and Y. So the spring force will be K, A theta 1 minus theta 2. So you can say this is X and this is Y. So that will be K X minus Y. And since A is common, it is Ka is theta 1 minus theta 2. Okay, and the weight, of course, because we add the weight here, this is by mistake. Okay, we add the weight because pendulum is supported vertically. So gravity is part of the weight should be part of the free body diagram. Okay, so those are, let me just put colors for the forces, arrows. This is a force here, and this is another force. For the pendulum on the left side, we have, again, mg, they are identical pendulums. They are identical, and the length is the same, L, A is the same, and N are also the same. So this is mg again. And we have here Ka. This is the same force, Ka This is by typing mistake here. Theta 1 minus theta 2. Okay, so the direction of the forces will be the weight downward and the spring force to the right. Okay, this is let's say 0.02 and this is 0.01, which are the pivot points. To get the equation of motion, you take moment about the pivot point to cancel the reactions. Okay, so here we have sum of moment about O1 equal to J1 or J theta 1 double dot. And as you know that J is for a bulk mass about O is equal to M times L square because JCG is 0 for bulk mass. Because this is a point mass. Okay, the forces, we take the counterclockwise positive, which is the direction of theta 1 and theta 2. Both are counterclockwise positive. Then the moment counterclockwise is positive. So we have ML square theta 1 double dot minus MGL theta 1 minus KA square theta 1 minus theta 2. So the force is mg, and you need the perpendicular distance. Okay, the perpendicular distance is L sine theta 1, and sine theta 1 is theta 1. Okay, so this distance is L theta 1. This is the perpendicular distance. So mg times L theta 1 minus, because it is clockwise, minus mg L theta 1. And the moment of this is of the spring force, you will multiply by the perpendicular distance, which is this value. Okay, this is perpendicular for distance, which is cosine, which is A cosine theta. So it is A, A cosine theta. For small theta, this is taken as 1. So we have cosine theta 1 equal to cosine theta 2 equal to 1. This is the assumption for oscillation. And sine theta 1 is theta 1, and sine theta 2 is theta 2. So the distance will be A, Ka theta 1 minus theta 2 times A. We will get Ka squared theta 1 minus theta 2. The same thing we will do for the moment, sum of the moment about O2 equal to J theta 2 double dot. And we get ML squared theta 2 double dot minus MGL theta 2 equal to minus MGL theta 2 plus Ka squared theta 1 minus theta 2. And then we put in matrix form right away before substituting for the solution. Okay, so we get ML square multiplied by identity matrix 1, 0, because J is the same for the two pendulums. Theta 1 double dot times theta 2 and theta 2 double dot plus the matrix. You arrange the equations in order. So you have, for the first equation, it is ML squared theta 1 double dot plus you take collect similar terms theta 1 theta 1, and we move them to the left hand side. So this will be MGL plus Ka squared multiplied by theta 1 minus Ka squared theta 2 equal to 0. This is the first equation. And the second equation we have ml squared theta 2 double dot minus the term that contains theta 1 is Ka squared minus Ka squared theta 1 plus mgl plus Ka squared times theta 2 equal to 0. Now you can put this in matrix form. The first equation has 0 theta 2 double dot. So this is why there is 0 here. And second equation has theta 1 double dot is 0. This is why there is 0 here. So this becomes a diagonal matrix. And the two terms on the diagonal are also equal. So this is ml squared is taken as common, multiplied by the identity matrix. The second matrix, you take, this is multiplied by vector theta 1 and theta 2. So it means that Ka squared, which is this term, minus the second term is minus Ka squared. And as you can see, again, we start with Ka with theta 1, so it is minus Ka squared. And then the last term is Ka squared, plus mgl. Okay, we call this matrix mass matrix. And we call this matrix stiffness matrix. The matrices should be symmetrical. Okay. And mass matrix should be positive definite, which means that its inverse, its determinant is not 0. Otherwise, you have no solution. Okay, so the mass matrix should be positive definite, which means the determinant is not 0. And stiffness matrix should be symmetrical. Both should be symmetrical. Okay, provided that you arrange the terms in order, that you start with theta 1, then theta 2, or x1 and then x2. Okay, now we can assume the normal mode solution, which is theta 1 equal to a1, theta 1, a1 cosine omega t, that is theta 1, or sine omega t, or the complex form a1 ei omega t. And theta 2 equal to a2 cosine omega t, or sine omega t, or you can use the complex form a2 ei omega t. Any solution you will use should be okay. And then when you substitute, you will get the determinant, and then you set the determinant equal to 0. Then you find the roots of the determinant, which is the characteristic equation. And so as we did with example number 1. Okay, so if we continue here in the example, the determinant, after we do the substitution, we will get minus omega square ml plus Ka square plus mgl. And this will be minus Ka squared. And here it is minus Ka squared. And the last term is minus omega square ml squared. This is also ml squared. Plus Ka squared plus mgl. Multiply by A1 and A2 equal to 0. 0 and 0. So as we said before, either A1 and A2 equal to 0, and this is a trivial solution, or the determinant equal to 0. A1 equal to A2 equal to 0 is trivial. Non-trivial is obtained by putting the determinant equal to 0. Okay, so the determinant, as you can see, we have this term is equal to this term. So this will be, the determinant will be squared, minus omega square ml squared plus Ka squared plus mgl, the whole thing squared, minus Ka squared equal to 0. So we can move the second term and take the square root. So this will be minus omega square ml squared plus Ka squared, this is squared, plus mgl, okay, squared, equal to Ka squared, or squared, right? Then you take the square root. When you take the square root, this will be plus minus. So when you take the plus step, so the solution will be minus omega square ml squared plus Ka squared plus mgl equal to Ka squared, or minus omega square ml squared plus Ka squared plus mgl equal to minus Ka squared. Yeah? Then this will be simplified, that Ka squared and Ka squared will cancel out. And then you get, and also that when this is cancel out, it means you can divide by L and divide by L here, divide by M and divide by M. So this will give us that omega will equal to G over L. This is omega squared will equal to G over L. And omega becomes square root of G over L. The second equation, we will move Ka squared to the other side. I mean, minus Ka squared to the other side becomes 2Ka squared. And this will give us omega equal to square root of, when you divide by ml squared, this will be G over L plus 2K over M okay, A square over L square. This is, as you can see, omega 2 is G over L plus, so this will be omega 2. This is bigger than omega 1 equal to square root of G over L. So those are the natural frequencies that is given here. Okay, so omega 1 is square root of G over L, omega 2 is square root of G over L plus 2K over M, A square over L square. Those are the natural frequencies. The amplitude ratios are obtained by substituting in, in the algebraic equations. Okay, so the amplitude ratio equation will be from, you can get the first one or the second, from the first equation or the second equation. So that A1 over A2 equal to Ka squared divided by minus omega squared ml squared plus Ka squared plus mgl. So to get the amplitude ratio, number one, it means you substitute for omega equal to omega 1. So Ka squared divided by omega 1 squared is G over L times ML squared plus Ka squared plus MGL. So this becomes 1. And as you can see, this 1L will cancel with 1L, and the whole term here will cancel with this one. So it becomes Ka squared over Ka squared, which is 1. The second mode or amplitude ratio is obtained by substituting for omega equal to omega 2, which is Ka squared divided by minus omega squared, which is G over L plus 2K over M A squared over L squared multiplied by ML squared plus Ka squared plus MGL. Okay, so 1L will cancel with 1L here, and this L will cancel out. And when you take MGL inside the bracket, this will cancel with this term. And M here will cancel with M. We have okay, and this will be we have L squared extra term. Okay, let me simplify. This will be equal to Ka squared, and this will be minus 2K A squared multiplied by L. Okay. I have L extra here. This should equal to minus 1. Wait, there is A here. A squared. No, this should cancel out. Okay, this is my mistake. This is L squared. Okay, so this will, the whole term will cancel out. This is L squared will cancel with L squared. Okay, and one L will cancel out only, and there will be L. So this will be minus 1. There is no L here. So this is equal to minus 1. Okay, so the amplitude ratio for the second frequency is minus 1. And this has some meanings that for the first mode, when omega equal to omega 1, the amplitude ratio is 1. A1 over A2 equal to 1 means that A1 equal to A2. And when A1 equal to A2, we go back to the system, theta 1 will equal to theta 2. Theta 1 will equal to theta 2. In this case, the spring is not loaded because the two ends are moving in phase with the same amount. So the spring, if you remove the spring, it is going to do the same thing. This is the simple mode. This is the first mode, which correspond to the two springs become as one simple pendulum. Okay, so this is the first mode. Okay, so here we have in phase and A1 equal to A2, the spring is not active. And when A2, for the second mode, we have A1 over A2 equal to -1. So they are equal. This is out of phase. And that A1 equal to minus A2. And the spring will have a node in the middle. Okay, so this is a node here. Thus, in the first mode, the two pendulums move in phase and the spring remains unstretched all the time. If the system is oscillating in the first mode, there is no load on the spring. In the second mode, the two pendulums move in opposite direction, and the coupling spring is actively involved with a node at its midspan. Consequently, the natural frequency is higher. Okay, so this is why we call it omega 2. There is omega 1 and omega 2. Okay, so in the first mode, the spring is only translating. So this value is 1. This value is also 1. Or if it is moving to the left, this value is 1. And this value is, -1. And this is -1. So there is no load on the spring. And second mode, we have when the spring is here, there is a node in the middle where the spring is, this node is 0. So if this is 1, and this is -1. Okay, and if this is -1, okay, this will have 1. And this node is always 0, or this point has always 0 deflection. Okay, so this will be the end of lecture 2. Any questions? All right, we'll see you inshallah on Thursday. And Thursday we will have the experiment as well at 3 o'clock. All right, yeah, master.